Hello and welcome. In this video, we're going to talk about the decision trees. Decision trees are considered to be the most intuitive models. So we've discussed about a couple of other intuitive models, but decision trees are so simple that even if you do not have a formal training into analytics, you can still be using decision trees. From your audience perspective, decision trees are very friendly. And they're also friendly for the people conducting analytics, and we'll discuss that in some time. Let's get started. So how does it look like? This image looks like a tree, right? Somewhat like a tree. But we are not interested in seeing things the way they appear on the surface. In analytics, we often want to explore a little further. And let's say in this case, we choose to turn this upside down, which means we've got the root on the top and we've got the leaves at the bottom. And this is how we'd mostly be using it for analytical purposes. So let's assume we want to use this kind of a structure for making our decisions. First of all, we'll have to give some signs here or legends. What are these? To the left, let's say we are saying is a yes, and to the right, we are saying is a no. So that's the legend that will be followed all across. These points that you see here are in general referred to as nodes. The topmost is called the root, and the ones at the bottom are called leaf nodes. And in between anything that you have are just intermediary nodes. They will not be called root, they'll not be called leaf. Another terminology could be that you can call this as a parent to these nodes, and this node is a parent to these nodes. So they have a parent-child kind of relationship as well. That's again a terminology you'll often hear being used. So let's start with a problem where we want to make a decision using this kind of structure. So let's say a few students approach an institute and they want to learn data science. How would the institute go about making that decision? We're just trying to replicate some logic here. It may not necessarily be a strict logic that's followed. It's just for our example. So let's say the first question that the school wants to ask is, have you studied mathematics till graduate level? To the left, you have the path, which results when your response here is a yes. To the right, you have the path, which results when the response here is a no. So let's say this question is being asked to 100 students. 75 of them said yes, and 25 of them said no. Now we have to further make our decision, and let's follow this path. So for these people who have studied maths till grad level, we'll ask another question. Are you familiar with any programming language? And this question is being asked to these 75 people only, right? So we're asking if you are familiar with any programming language. Once again, we'll get a response. Let's say out of 75, 50 of them said yes, because left is yes and right is a no. That's the convention we are following. So 50 of them said yes, they've studied the programming language. Who are these people? Who have studied mathematics to grad level and they've also studied some programming language. Then comes the decision. You can join the data science course. What about these people who have studied maths but do not have a programming background? We are saying you can join a preparatory course in programming. So you can see how this logic is being applied at each time you're asking questions and arriving at a decision. Well, believe it or not, we actually end up doing this multiple times during the day intuitively. For example, if you're leaving from home to work, and let's say there are two possible routes to go to work. If you check traffic and you find that one of the routes is quite crowded, won't you take the alternative path? That's again a decision. It's like at a node, you ask the question, if the traffic is high, you're taking a different route. If it's not, then you take the routine route. If it's a Friday evening, you may indulge into some binge watching. So you ask yourself intuitively, what day is today? Do I have to go to work tomorrow? No. If no, then maybe I can spare a couple of hours watching my favorite shows on the OTT. That's again a decision. That's just a one node. But there could be such cases when we have multiple nodes connected. Anyway, let's continue with our discussion to the right of this root node. So these are the people, these 25 people are not math graduates. What are the options for them? You'll ask them a question. Are you ready to dedicate at least 15 hours per week for self-study? Because if you do not have a necessary background, you may have to dedicate more time. If the response to this is a mix, 20 of them say yes and 5 of them say no. Those who are willing to put in the time, you may put them to a foundation course. But those who are not even willing to put the time and don't even have the necessary background, you can just tell them you may consider it later, whenever you have time. So you can see logically how we have arrived at the decision. It's a simple example, but I hope you intuitively understand. Now, where did we actually use any heavy term coming from maths here? We are just doing what is super logical. That's where I said decision trees are very easy to comprehend for your audiences. They don't need a formal training to be able to decode a decision tree. But let's just understand this now from data perspective. How would this data look? So we have captured the same information that you saw there in the form of some features. So we have an applicant ID. This is the student ID. Then we have captured whether the person is a math graduate or not. Then we've captured whether the individual has a programming background or not, and whether the person is willing to allocate sufficient time for self-study. And as a result, we have the final acceptance column. So anybody who cannot be enrolled for any course, for example, neither data science, nor the preparatory, nor the foundation, would only be put as a no here. Rest all will join some or the other course. Let's understand some of these observations, how these are mapped to a tree so that you learn how to read a decision tree. Let's take the first observation. This person is a math graduate, has a programming background. In this case, most likely this self-study would not even matter because that comes to the other branch of the tree and you have an acceptance, yes. Let's map this to the tree. So we are saying the person is a math graduate. We go to this node. Then we are saying person also knows the programming language. So we come to this part. So notice in this case, while the self-study option is captured in the data, it is not really helping us make a decision. Decision has already been arrived at using the background in terms of education and program. Let's take the second record. This case shows it's a math graduate, does not have programming background, and self-study is a no. Once again, it probably would not matter in this case what's the allocation to self-study as per our logic, because we are going to be arriving at a decision just based on math graduate and programming background. And we will probably admit this person to a preparatory course. Let's see. So the person is a math graduate, that's fine. But here the decision becomes a no. So you go to this branch and you'll say you can join a preparatory course. Just one more example. This is a case where the person is not a math graduate, which means to begin with, we are not going to the left of the root node. We are going to the right of the root. And interestingly, this person has a programming background, but probably this programming background would not be a decision-making factor as per our tree, our logic. This person is not willing to dedicate enough time for self-study. So if you do not have a background and you're not dedicating enough time, you'll most likely not be offered admission. Let's see, how does it work? So this person is not a math graduate. We come to this node. We ask this question, are you willing to put enough time? This person says no. Then we're just simply saying you may consider it later. In this case, the programming background did not matter. So this is how the decisions are arrived at. When you pass a data, the tree would build on some logic internally and it would check for appropriate variables and arrive at a decision. Like I said, this is just an example. This is not what is followed as practice while deciding whether somebody should be admitted to a data science course or not. But just for illustration purposes, we use this here. Now you may be wondering, how do we actually decide which variable should occupy this place? Which variable should occupy this place? Which variable should go here? I mean, this was a solved problem, but how does the algorithm get to know which variables should be taken as a priority to split on and further choose the next variable to split on and so on? And let's understand that with the help of an example. So here's our data. In order to arrive at this decision trees use the concept of Gini gain. We'll first understand Gini impurity, Gini index, and then we'll talk about the Gini gain. How does it work? Remember, every algorithm would always have a logic. In linear regression, we saw the minimum sum of squared errors. In logistic regression, we saw another objective function, which was maximum likelihood. Similarly, decision trees use Gini gain. So let's take the target column, which is our column that we are interested in predicting. This is the acceptance. Focus on this column only, and let's try to answer a few questions. Can we clearly look at the data and say, in this small subset of the overall data, the probability of a candidate getting accepted is 8 by 10? How? Because out of 10 opportunities, 8 times, 1, 2, 3, 4, 5, 6, 7, and 8, 8 times we have an acceptance. So the probability of getting accepted is 8 out of 10. Probability of getting rejected, then obviously would be 2 by 10 because there are only 2 possibilities. If out of 10 times, 8 times there's a selection, then 2 times there will be a rejection. So using these probabilities, we can calculate the Gini value. What is that? 1 minus the probability of success squared minus the probability of failure squared. We can put these values here. So we can calculate the Gini root is 0.32. Why are we calling this as Gini root? Because so far we have not done a split on any other variable. We are only looking at the acceptance. This value is 0.32. Now, we will choose the variable which gives us highest difference from this value. Next, we will choose each variable along with the target column and calculate Gini for it. Let's see how does it work. So let's say we take the first variable, which is math graduate. Now we have to concentrate only on this column and this column. So let's first highlight those rows only in the data where this person is a math graduate. Yes, these are the 6 rows, 6 rows where the person is a math graduate. Now, out of these 6 opportunities, do we have any rejection? Well, it looks like for this data, with whatever we see right now, we don't find any rejection. So can we say that the probability of getting accepted, given that the person is a math graduate, at least for these 10 observations, is 1, which is a 6 out of 6? And likewise, the probability of getting rejected if the person is a math graduate for these 10 observations that we see, particularly the 6 highlighted observations, is 0 by 6. Similarly, can we answer these questions for the scenarios where the person is not a math graduate? Let's first highlight only those rows where the person is not a math graduate. These are the 4 rows, but you see a mix here. So all these cases belong to those learners who are not math graduates, but 2 of them got selected. So there is 1 by 2 or 50% chance of being accepted or given admission, even when the person is not a math graduate. Probably this person would have opted for a foundational program, or maybe was willing to put enough time. We saw that logic. So based on this, we can easily calculate these probabilities. Now we have to calculate the Gini values for both the cases separately. Let's say when the person is a math graduate, what is the answer? 1 minus probability of success squared minus the probability of failure squared. We get this value as 1 minus 1, this will be 0. Similarly, when the person is not a math graduate, what happens in that case? 1 minus 1 by 2 squared minus 1 by 2 squared, because both the cases were same in terms of probability. So we get this value as 1 minus 1 by 4 minus 1 by 4. So this will be 2 by 4 or 1 by 2. 1 minus 1 by 2 will be 0.5 or 50%. So let's just focus on these 2 levels right now. We are working on a column called math graduate, and we have 2 levels here, yes or no, and we have the Gini values for both. So how do we calculate the overall Gini value for math graduates? Right now, we have calculated it separately for a graduate yes and graduate no. The overall value will be calculated as a weighted average. So there were 6 cases out of 10 where the person was a math graduate, and there were 4 cases out of 10 where the person was not a math graduate. We are multiplying the corresponding Gini values with both the cases, and we get the outcome as 0.2. Now that we have computed the Gini value for math graduates variable, we have to calculate its difference from the root. The root value we computed some time back was 0.32. So if we subtract the Gini value for math graduate from the Gini value for root, we'll get 0.12. Now, this is the Gini gain. Essentially, the concept of Gini is that we should not have a dilemma. We should move in one direction. So whichever variable gives me the highest Gini gain, that's kind of a representation of increase in impurity. What do we mean by impurity? You are moving towards dominance of one or the other category. So you may have a majority of a yes or a majority of no, but having yes or no equally at a node is not considered good. So Gini, just like entropy, is another way which helps you move towards a decision, where you move away from a scenario where you're stuck at making decisions. We need to repeat the exact same steps for the variables like programming background and self-study as well. I'm not doing those calculations here because I just wanted to demonstrate how does it work. Now, which variable would be chosen for the split? The variable which has the highest Gini gain. So these variables are all competing at each level, at each node for the split. Whichever variable has the highest Gini gain is the one that's chosen for the split. You can try those calculations on your own and see which is the right variable. We might have created a tree based on larger data. Right now, we are talking about just these 10 observations, just for illustration purposes. Now, moving on to the assumptions related to decision trees. The slide is quite clean. It says all good. And remember, in the beginning, I said decision trees are also the favorite of the people who practice analytics or data science. Why? Decision trees are not sensitive to outliers. Decision trees do not really require you to scale the data. And decision trees also do not worry about multi-collinearity. Decision trees do not assume that there is any specific distribution. So they are free from all sort of assumptions and pretty good at making decisions. So without worrying for the typical assumptions, like you have with the conventional models, you can simply go ahead and apply decision trees to solve a problem. While the example that we took was for a classification problem, the decision trees can also be used for solving the regression type of problems. But one word of caution, decision trees require pruning. Pruning is a term that comes from gardening. In technical terms, we may say that this is hyperparameter tuning. So there are certain controls that the person who is designing the model would want to pass as the inputs to begin with when working with decision trees. We will see more of these when we do our hands-on exercise. But the typical hyperparameters are max step, So to what extent do you want your tree to grow? For example, we saw only a couple of branches. We asked one or two questions and then we made a decision, but this could go on for a greater depth. Similarly, there is something called as min sample leap. So what is min sample leap? It decides the point beyond which you will not split the node any further. And then we have min sample split, quite opposite of min sample leap. It decides the minimum number of observations in a node for it to be considered for a split. If we don't tune these hyperparameters properly, then we face a problem that's known as overfitting, which means while training the model, it might work pretty well. But when you're trying to evaluate it on the test data, it may not give suitable results. That's a very common problem with decision trees.